Hey, in this video I'm going to be showing you how to convert from Cartesian coordinates to cylindrical coordinates and how to do triple integrals using cylindrical coordinates. So if you have a point defined using Cartesian coordinates, and let me draw projections so that you know where exactly the point is. So this is the x coordinate, the y coordinate, and the z coordinate. And if we want to convert this to cylindrical coordinates, we use r, theta, and z. And this z is exactly the same z. It's the distance along the z-axis. So if you want to find r and theta, we look at the projection of the point on the xy plane, which is going to be this dot over here. And we say that this point is at a distance r from the origin. So this distance here is r. And we say that this radius r is at an angle theta from the positive x-axis, exactly like in polar coordinates. So from this we can say that x is equal to r cosine theta, y is equal to r sine theta, and that x squared plus y squared is equal to r squared. So if you have a triple integral in Cartesian coordinates, function of x, y, z, and then you integrate, dz, dy, dx, or any other order over the region R, we can convert to cylindrical coordinates. It's the same region, but instead of defining the function in terms of x, y, and z, we're going to define the function in terms of r cosine theta, r sine theta, and z. And then we have r dz, dr, d theta. Now this r over here is the Jacobian of cylindrical coordinates. It's the same Jacobian of polar coordinates. And whenever we convert from one coordinate system to another, we have the Jacobians. And I talk about Jacobians and general change of variables in another video, so you can check this out. Okay, so let's have an example and see how we can integrate using cylindrical coordinates. Okay, so we want to find the volume of the solid bounded by z equal to 0, z equal to h, and x squared plus y squared is equal to r squared. So x squared plus y squared equal to r squared, that's just an infinite cylinder. So at the xy plane, there's going to be a circle of radius r. And since z is not restricted, z could go from positive to negative infinity, and this becomes an infinite cylinder. And then we have z equal to 0, which is the xy plane, and z equal to h, which is an infinite plane at height z equal to h. So our solid becomes the cylinder of radius r and height h. So this becomes our solid. And we can say that the volume is equal to the integral 1 times dv. Now we're going to be using cylindrical coordinates, so we say that the volume is equal to the triple integral 1 times r dz dr d theta. Now we need to find the limits of integration. So for the z, you sketch arrows going in the positive z direction, and you see that you always enter the region through the plane z equal to 0, and you always exit the region through the plane z is equal to h. Now we want to find the limits in terms of r and theta. So we look at the projection of the shape on the xy plane. See that the projection of the shape on the xy plane is going to be a circle of radius r, like this circle here. And want to find the limits in terms of the radius. So we start at the origin and go radius outwards. You see that the region is always defined at r is equal to 0, and that we exit the region and the value of the radius equals to r. So r ranges between 0 and r. And finally, since this is a complete circle on the xy plane, theta ranges between 0 and 2 pi. So now we can integrate. So we're integrating 1 times r with respect to z, so we're going to get z r evaluated at 0 and h. It's going to be hr. So now we're integrating from 0 to r, from 0 to 2 pi, hr dr d theta. So if you integrate hr with respect to r, we're going to get hr squared divided by 2, evaluate at 0 and r. So we get hr squared divided by 2. Now we integrate from 0 to 2 pi, hr squared divided by 2 d theta. So we get hr squared divided by 2 times theta. Theta evaluated at 0 and 2 pi. So we end up with hr squared divided by 2 times 2 pi. The 2's cancel, and we get that the volume is equal to pi r squared h. And that's the volume of the cylinder.